Okay, good afternoon. I'm Emanuela Formaggio from Department of Non si sente? Okay, good afternoon. I'm Emanuela Formaggio. Non si sente? Non si sente? Così? Okay. I'm Emanuela Formaggio from Department of Neuroscience. And it's a pleasure for me to introduce the second part of the oral section about biomedical signal and image processing. And the chairs of this session will be Professor De Marchis from University of Messina, Professor Ambrosini from Politecnico of Milano, and Professor Mayburger from Politecnico of Torino. Okay, thank you.
So I think we are, good afternoon to everyone. I think we are going to start with this session with a video presentation because the presenter is not here. And the presentation is from Caterina Iskra. So the title is Discriminatory Power of Global Longitudinal Strain and Left Ventricular Ejection Fraction for Identification of Dilated Cardiomyopathy.
Good afternoon to everyone. I am Caterina Iskra, a PhD student of Biomedical Engineering Group of Trieste, and I'm sorry that I couldn't present personally my work as I am on maternity leave. The topic of our study is discriminatory power of global longitudinal strain and left ventricular ejection fraction for identification of dilated cardiomyopathy. And the study was conducted in collaboration with the cardiovascular department of the Trieste University Hospital. So, dilated cardiomyopathy stands as a major cause of heart failure and the most common reason for heart transplantation worldwide. The left ventricular ejection fraction is one of the most used parameters to assess heart function and predict outcomes in DCM patients. But despite that, diagnosis of these patients can be challenging, in particular in the early asymptomatic phase. This because the left ventricular ejection fraction may not be sensitive enough to detect subtle changes in ventricular function during the early stages of DCM, and at the same time the cutoff values are inconsistent. Indeed, there is a lack of standardized lower cutoff values for defining abnormal left ventricular ejection fraction in DCM. For all these reasons, additional parameters and clinical factors need to be considered for accurate risk stratification in DCM patients. Addressing these open problems may involve incorporating other modalities, such as strain imaging, for example, global longitudinal strain, or cardiac magnetic resonance imaging, to complement left ventricular ejection fraction measurements. Additionally, also parameters extracted from heart rate variability demonstrate considerable potential as parameters for DCM assessment. Therefore, we aimed to investigate discriminatory power of global longitudinal strain and left ventricular ejection fraction as a feature of logistic regression models for identification of DCM. So, in this study, we analyzed clinical data and processed ECG signals of 276 subjects. In particular, the study encompassed 138 patients affected by DCM and 138 healthy controls. The left ventricular ejection fraction, which reflects pumping heart efficiency, has been obtained by the Simpson biplane method. Instead, the global longitudinal strain, which assesses the deformation or strain of the myocardium, has been obtained by speckle tracking echocardiography. Furthermore, all subjects underwent a 24-hour Holter ECG recording using the ambulatory electrocardiographic recorder SpiderView, with a sampling rate of 200 Hz. The RR intervals were extracted and labeled by using ScienceScope analysis software, and the data was analyzed using a MATLAB program that evaluated the RR segments of 300 seconds. These segments were interpolated with cubic spline and resampled at 2 Hz, producing the total HRV signal. Following that, linear and nonlinear HRV features were extracted for each segment. After that, 2 different feature sets were considered. The first one, composed by the global longitudinal strain, HRV features, age and sex, and the second one with the left ventricular ejection fraction, HRV features, age and sex. In both cases, the most discriminatory features were selected using information gain as criterion. Subsequently, 2 models were produced by logistic regression algorithms. The first one, the logistic regression GLS, using first set of features, and the second one, the logistic regression LVEF, using second set of features. Moreover, the performances of the classifiers were estimated using 5-fold cross-validation, and average metric values were calculated. Finally, the nomograms have been created and used to improve interpretation of obtained models. So the results of features selection analysis showed that the most informative features for classification between DCM and healthy controls listed from higher to lower information gain coefficients were global longitudinal strain, ratio between short-term variability and long-term variability of the RR sequence, so the SD1, the ratio between SD1 and SD2, root mean square of the square differences of successive RR intervals, RMSSD, beta exponent, and normalized low frequency power for the first model, so the logistic regression GLS model, and left ventricular ejection fraction, ratio between SD1 and SD2, RMSSD, beta exponent, and normalized low frequency power for a logistic regression LVEF model. The performance was higher in the model based on HRV features and global longitudinal strain compared to the logistic regression model constructed with the HRV features and left ventricular ejection fraction. In particular, the model that includes global longitudinal strain as a feature showed an accuracy of 86%, so a slightly higher accuracy with respect to the model mainly based on left ventricular ejection fraction that presents an accuracy of 83%. Finally, confusion matrices show that DCM patients were correctly classified with 88.3% and 86.3% with logistic regression GLS and logistic regression LVEF models, respectively. Finally, here are depicted the produced nomograms for the 2 models, and the importance of global longitudinal strain, left ventricular ejection fraction, and HRV features has been confirmed yet again by the nomograms. In particular, we can observe that the clinical parameter, global longitudinal strain or left ventricular ejection fraction, appears to be the most significant in the differential classification between DCM and healthy controls in both nomograms, supporting the literature that suggests these 2 measures are the most helpful in the diagnosis of this condition. As I said before, the nomograms also reveal the importance of the HRV features. In particular, beta exponent measures the relationship between the frequency and power spectrum of the RR interval, providing an index of the HRV signal's long-term scaling properties, which may change in DCM and so potentially aid DCM diagnosis. Normalized low frequency power is often associated with the joint action of the vagal and sympathetic system that can alter it in DCM patients. RMSSD is an indicator of the irregularities of the heart rhythms, also characteristic of DCM, and the ratio between SD1 and SD2 describes diastolic blood pressure, which appears to be more variable in DCM patients than in healthy subjects. So also these three parameters can partially support the differential diagnosis between DCM and healthy controls. In conclusion, the study results underscored the discriminative ability of both non-invasive global longitudinal strain and left ventricular ejection fraction parameters, along with the potential usefulness of HRV features, particularly beta exponent, in assisting the diagnosis of DCM. So thank you for your attention, and I am looking forward to meeting you soon at one of the GNAB events. And feel free to write me regarding this study. Thank you again.
So the next speaker is Esther Bruno, and she from Università di Pisa, and she's going to present a study about entitled Hessian-based neck tracing of dendritic spines, a preliminary study on confocal images.
Good afternoon. I'm Esther Bruno, and I'm a PhD student in biomedical engineering at the University of Pisa. And today I'm going to present a preliminary study on spine neck tracing. Okay. So, quantify neuromorphology at the micro and nano scale, and so dendritic arborization of the neurons and spines characterization is still is a challenge in cellular neuroscience. The goal is to automatically delineate the isolate neurons and subneural structures in order to delineate the link between the functionality and the morphology of the neurons, and to understand what happens at the cellular scales when neuropathies are present. And images from ex vivo samples, like human samples and murine samples, are characterized by dense packed neurons. And this means that this makes the task really difficult. Why are we interested in spines? Spines are neural protrusion implied in synaptic function and support learning and memory. Neuroscience are particularly interested to quantify their shape, their different shape, and their numbers. Indeed, it is well known that their numbers change in aging and in neuropathies, such as schizophrenia and autism, as you can see in the graph. But to pursue our goal, we have to face some issues. Like the first one is the high density of these images from ex vivo samples. Then we have the low contrast to noise ratio due to the different image technique. And then we have the challenging detection of the spine neck with conventional microscopy due to the diffraction limit. So in previous studies, we see other spine neck reconstruction based on, for example, large database of images to create a library of models or to train a convolutional neural network. Other studies are based on local geometrical models or legend functions. Our approach is a new approach based, divided in few steps. We first start from the original image, and we perform a segmentation based on the intensity distribution of the image, applying a Otsu method. And we obtain a segmentation of the main body of the dendrite and the spines. As you can see, most of the necks in the segmentation are missing. So that's why we apply our new approach for neck tracing to reconstruct the neck in terms of a track and no segmentation. And we then validate our results with a gold standard that is constituted by a semi-automatic segmentation reconstructed manually using the Imaris software. Our dataset is a confocal image stack of pyramidal neurons of human samples. And this dataset is available online, is free available. And it was acquired from a group of the Professor De Felipe in Madrid. So, tracing a neck consists in connecting two disconnected clusters. One is linked to the spine head, and one is linked to the dendrite. The process is divided in two phases. Phase one is the phase that finds the starting voxel, which from which the algorithm starts. And in figure we can see the starting voxel in green, and then we define the outer border of the spine head in yellow. We test 3 different criteria to select this first voxel. The first criteria is based on to find the voxel with the minimum distance from the dendrite that is expressed in terms of Euclidean distance. Then we have the second criteria that find the voxel with the maximum intensity. And then the third criteria select the voxel intersected by the principal axis of the head. We move to the phase 2, and for this phase, we focus our attention on the Hessian matrix. Hessian matrix allows to describe spatial distribution of the images. And we calculate for each voxel of the trace, the Hessian matrix, and then we extract from the matrix eigenvalues and eigenvectors. Why? Because we are interested in to reconstruct spine necks. Spine necks are considered tubular structure, and we know that Hessian matrix and the eigenvalues of the Hessian matrix, the smallest one of these eigenvalues is the one that define is the one along the axis in which the tubular structure grows. So we are in the second of the figure. We are in the second option, in which the tubular is the neck, and we pick the smallest eigenvalues. We use this procedure at each step of the phase 2 because it's a one voxel step procedures repeated iteratively. So for each voxel in the trace, the eigenmatrix and the Hessian matrix with the eigenvalues are extracted to define the complete trace of the neck. Here we have some results of our reconstruction. In red, you can see the segmentation. In gray, I know it's like invisible, but you can see the reference segmentation, the gold standard they use as reference segmentation, and then the next reconstruction by the algorithm. So how we validate our results? We use a manual, a distance, a measure, DRS, That basically is the distance from of the neck, of each traced neck from the reference segmentation that is displayed in green. The border of the reference segmentation are in green. So we evaluate this distance, and when this measure is 0, means that all the voxels in the neck overlap with this segmentation. So we evaluate this distance for all the 3 initialization criteria of phase 1. And from these preliminary results, the best criteria seems to be the second one, in which 80% of the neck keeping an average distance of less than 1 voxel from the reference segmentation, and half of them are overlapping with the reference segmentation. On the same information, we, of the Hessian metrics, we developed a new algorithm called SEMPI, which imply k-means, iterative k-means in a 4D space, based on the intensity of the image and the second-order derivatives. So we, in this case, we are interested to delineate the dendrites. That in this case, the tubular structure are the dendrites. And that's why we apply SEMPI, which improve neural reconstruction, including volumetric and morphological information. With SEMPI, we obtain a segmentation at the microscale and the nanoscale. At the microscale, we identify the tubular structure of the dendrite, and we delineate all neurons. At the nanoscale, we apply SEMPI to to perform a spine segmentation, and we obtain comparable results to the manual one, but the necks are still missing. That's why, in the future, what we want to do is to integrate SEMPI segmentation with the neck tracing approach in order to have a robust tool for the complete segmentation of the neurons at the micro and the nanoscale. And this work has been performed within Sensei, that is a project and is a partner of the Human Brain Project. And in particular in PISA, we focus on the development of algorithm and spines isolation. Thank you for your attention.
Thank you. We'd like to invite the next speaker, Serena Moscato from the University of Bologna, with the title of Autonomic Response to Virtual Reality in Oncological Patients in a Real-World Context.
Good afternoon, everyone. Thanks for the presentation. I am Serena Moscato, postdoc researcher from the University of Bologna, and I'm going to present you the results about the evaluation of autonomic response to virtual reality in oncological patients in a real-world context. Virtual reality is one of the most innovative technologies developed in the last decades, and it can generate a virtual scenario, making the user feel completely immersed in it. Virtual reality is primarily enjoyed by using VR headset, and they are usually coupled with a controller to interact with the virtual environment. Of course, virtual reality is mainly known for entertainment purposes, but in recent studies have demonstrated the positive impact of virtual reality in relieving from unpleasant sensations such as pain, anxiety, and depression in different clinical settings, such as in case of psychological distress, during invasive procedures, and in rehabilitation settings. Distraction appeared to be the main effect, the main mechanism behind the effectiveness of voir in relieving from unpleasant sensations. Indeed, voir is capable of emotionally involve the subject, the user, making him feel a sense of presence within the virtual environment and capturing his attention and directing it towards positive stimuli. On this basis, Fondazione Ant, an Italian NGO, which provides patients with health assistance directly at home, designed the Look of Life 2.0 project, whose aim is to integrate the virtual reality in its clinical practice in order to relieve cancer patients from the cancer-related psychophysical symptomatology. We have already conducted, together with Fondazione Ant, a pilot study by giving patients a VR headset to be used at home. And based on the promising results obtained by this first pilot study, we designed a new randomized control interventional study in order to better assess the effects of virtual reality. Virtual reality, indeed, is perfectly suited for this kind of application, since the patient can autonomously use the VR, since it doesn't require any specific training, and it can be used also in case of poor mobility. VR can be seen as an off-the-shelf tool to be used as a distraction method when there are negative emotions and unpleasant sensations arising. But how to evaluate the effects of the VR? There are two sets of methods available. The most common ones are the explicit methods that rely mostly on interviews and questionnaires. So basically by asking directly to the user how the VR experience was. Besides that, we have also available the implicit methods relying on a behavioral assessment of the VR experience, so without the direct involvement of the user. And a way to carry out a behavioral evaluation is by monitoring the physiological reaction to VR. How to monitor the physiological reaction? It is possible by monitoring the so-called autonomic signals, meaning all those signals that are strongly affected by the one or both branches of the autonomic nervous system, so the parasympathetic and sympathetic one. Two examples of autonomic signals are the photoplethysmography, or PPG, which represents the variations occurring in the blood flow at each heartbeat, and the electrodermal activity, representing the electrical conductance of the skin changed by sweat secretion. The silver lining of these two signals is that they can be recorded also by using wearable devices, so allowing monitoring in daily living and not only in a controlled environment. So, starting from this background, the aim of this study was to assess the autonomic response to virtual reality in advanced cancer patients involved in a palliative care home program. The study has been designed as an interventional exploratory randomized control trial. Participants have been randomized either in the experimental group receiving the VR headset or in the control group receiving a tablet. For both two groups, the study lasted 4 days, and as explicit methods we administered to the patients at the beginning and at the end of the study the hospital anxiety intervention scale and the brief pain inventory, while the patients were also asked to fulfill the digital version of the Edmonton Symptoms Assessment Scale directly through either the VR headset or the tablet. Only for the experimental group, we also monitored the physiological reaction with a wearable device worn at the wrist. So let's focus on the experimental group. Here's the details of the two devices. As a VR headset, we used a Lenovo Mirage Solo. We uploaded into the headset 2 different types of contents, an interactive content specifically developed for this project, and a selection of non-interactive immersive contents. While as the wearable device, we used the Empathic i4 wristband. There is a medical grade wearable device that can record a total of 4 physiological signals, but for the purpose of this study, we used the PPG and the EDA for further analysis. By collecting the log file from the VR headset, we detected on the physiological signals recordings 2 time instants, the starting point and the ending point of the VR session. Based on these 2 time instants, we defined 3 different phases: a VR phase lasting from 3 to 5 minutes, and then a pre-VR and a post-VR phases, both lasting 5 minutes. Then going to the signal processing part, for the PPG, after having applied a bandpass filter, we applied a literature algorithm to segment the PPG signal into PPG pulses. These PPG pulses were then be subjected to a signal quality check algorithm, and by retaining only the good quality PPG pulses, we estimated the interbit intervals then further used to conduct an heart rate variability analysis. While regarding DDA, after having applied a low-pass filter, also in this case, we applied a signal quality check algorithm found in the literature, and another state-of-the-art algorithm has been used to decompose the signal into the tonic and the phasic component. And from the EDA signal, we analyzed the whole signal, the tonic, and the phasic components. For each of the 3 phases, we extracted 21 features, 10 coming from the heart rate variability analysis and 11 coming from the EDA analysis. And in order to assess whether there were any differences by comparing the 3 different phases, we used linear mixed effect models, modeling the physiological features as the outcome variable, and by setting a fixed effect representing the different phases, pre-war, war, and post-war phase, and 2 random effects representing the subject and the session that instance is referring to. And then finally, we apply a marginal F-test to assess if there was any statistically significant difference. We collected 61 VR sessions coming from 27 patients, but after applying the signal quality check algorithms, we were able to retain only 28 sessions to conduct later on the heart rate variability analysis, and 50 sessions for the EDA analysis. As a result, by setting the pre-war phase as reference value for the heart rate variability analysis, we found a significant decrease in the ratio between low frequency and high frequency during the war phase and post-war phase, and a significant increase of the approximate entropy in the post-war phase. Regarding the EDA analysis, we found a significant increase in the mean values of the whole EDA signal and of the tonic component, concurrent with a decrease in the frequency of the phasic component's peaks. By commenting these results, the decrease of the ratio between low frequency and high frequency, representing the sympathovagal balance, could be ascribed to a greater activation of the parasympathetic branch over the sympathetic one. There is an agreement with a more relaxed state of the participant while using the VR. While for the approximate entropy, representing the complexity of the heart rate time series, the increase in this physiological feature can be seen as the higher capability from the cardiovascular system to more easily be adapted to changes. For the EDA analysis, lastly, a concurrent increase in the mean values of the EDA, the whole EDA signal and of the tonic component that basically carry the same information, together with the decrease with the frequency in the phasic components peaks, we hypothesize that this can be seen as a higher arousal and engagement of the participant given by the voir experience, together with a less stressed state. In conclusion, the aim of the study was to investigate the autonomic response to voir in oncological patients in a real-world context. To the best of our knowledge, this is one of the first attempts in conducting this kind of assessment in a real-world scenario, demonstrating that PPG and EDA are sensitive to the voir experience. And the features extracted from these two signals resulted in agreement both with previous literature and also with the explicit evaluations given by the participants. Further works are needed to overcome the limitations presented in this study. For example, we had a very limited data set due to the influence of the external noise caused by the uncontrolled environment. And we haven't controlled here several confounding factors that can play a role in modifying the behavior of both PPG and EDA signal. Plus, we haven't a uniform number of voir sessions from each participant, although we controlled in a way this source of variability by setting the subject random effect. And lastly, for technical issues, we weren't able to record the physiological response to the tablet in the control group. That would have given a such valuable insights about the reactions by using these two different devices. Anyway, despite these limitations, this study corroborates the findings already presented in literature that present the voir as a promising tool to be integrated with traditional psychological interventions to provide a quick relief from unpleasant conditions. Thank you very much for the attention.
So let's move to the next speaker, Andrea Costanzo, which is presenting the work Quantitative Validation of an Automatic Video PPG Technique During Autonomic Elicitations. The stage is yours.
Good afternoon, and today I'm presenting our work, Quantitative Validation of an Automatic Video PPG Technique During Autonomic Elicitations. First of all, I'd like to start with a brief introduction on video photoplatismography, which is a technique that allows the detection of blood volume variations in peripheral microcirculation by measuring slight periodical skin color variations through a camera. This technique does not require physical contact, and this can be a major advantage in some applications, such as neonatal intensive care unit, the monitoring of chronically ill patients, or telemedicine in general. Since it was first proposed back in 2008, many different approaches have been proposed for video PPG, but the general workflow remains the same. So we have, of course, the video recording phase, then the detection and tracking of a region of interest, and of course, signal extraction and processing to obtain a useful video PPG signal. In this work, we developed and validated a video PPG automatic method with the final goal of obtaining pulse rate variability parameters to be used as proxy measurements of heart rate variability. We validated each step of the pipeline, starting from the automatic skin detection, then the pulse-to-pulse series, and finally the pulse rate variability parameters thanks to an autonomic elicitation protocol. So moving to the experimental setup, we recruited 22 healthy volunteers with phototypes ranging from 2 to 4 of the Fitzpatrick scale. We selected the hands palm as the ROI, and which was recorded with an RGB camera at 115 frames per second in controlled illumination and background conditions. We, at the same time, recorded the finger PPG that was taken as the gold standard. So the first step of the pipeline is, of course, the region of interest identification and tracking. And we developed a completely automatic pixel classifier that allows the classification of a pixel of each frame as skin or no skin. And it is completely automatic, so it does not require the intervention of a human operator at any stage. The classifier is a decision tree and is specific for each video. So we need a different training set for each video, but after training we use the classifier to segment all the following frames. The starting point for this segmentation method was another method proposed by Barbieri in 2020, which is based on the k-means clustering algorithm. The clustering was used for the unsupervised labeling of the pixels of the first frame as skin or no skin. In our work, we added a preprocessing stage consisting of the conversion to the HSV color space and the principal component analysis. Of course, we validated this method and we created a validation set. We asked 4 subjects of the experimental population to record another video with free background and illumination. So we had 4 subjects recorded in the experimental condition and in uncontrolled conditions. We then extracted 4 frames from each video and we manually segmented them to obtain a ground truth. The evaluation metric was a dice similarity coefficient. And then we compare the performances with the algorithm that does not have the preprocessing stage, and in both the conditions, controlled and uncontrolled conditions. So in this slide we have the results of the validation, and we can clearly see that the algorithm proposed in this work achieved better performance and also a reduced variability, pointing to the improvement made by the preprocessing stage. Then there are the signal extraction and processing steps. We obtained a raw signal from the green channel of the segmented video, but the signal was affected by artifacts in the form of jumps, like the one in the red box, and also was affected by a nonlinear trend. We eliminated the artifacts and the nonlinear trend with a method that computed a series of breakpoints, the linear interpolance between them, and then subtracted the interpolance from the signal. Then we interpolated and bandpass filtered to obtain the video PPG signal. Then, thanks to the amplitude multiscale peak detection algorithm, we identified the systolic peaks and were able to compute the pulse-to-pulse series, both for the video PPG and the contact PPG, which was taken as a reference and, of course, was recorded at the same time. And we validated the pulse-to-pulse series with the Spearman's correlation coefficient, and the series that achieved a correlation lower than 0.65 were discarded. So the following analyses were conducted on 19 subjects out of the 22 initial subjects. The autonomic stimulation protocol we devised was made of a series of simple tasks that elicited some autonomic responses, specifically a vagal activation during pace breathing and a sympathetic activation during hand grip. In this slide, we have an overview of the selected PRV features that were validated in terms of correlation with the Spearman's correlation coefficient and agreement with the Bland-Altman analysis. So here an overview of the results. Regarding the correlation, the highest correlation was observed for the VNN parameter, while the lowest for the SDNN and PNN50. And also we observed a drop of correlation during hand grip. Regarding the agreement, so the Bland-Altman analysis, there was an almost null bias for the VNN and an overestimation by video PPG of the other parameters, except the sympathovagal balance, which was underestimated. Again, we observed during hand grip a larger dispersion of errors. Now we can focus on the sympathovagal balance, an overview of the correlation. As I said before, we had a drop of correlation during hand grip, especially during the first hand grip phase. And now the Bland-Altman analysis. We can observe the negative biases and the larger dispersion of errors during hand grip. We also observed the behavior of the sympathovagal balance during the experimental phases. So now we can see a prevalence of high-frequency components during pace breathing and the prevalence of low-frequency components during hand grip, which was absolutely expected. And these differences were found to be significant also with the multiple comparison test with Bonferroni correction, both in video PPG and contact PPG. Concluding, we can say that we increased the robustness of the automatic pixel classifier thanks to the preprocessing stage. And regarding the pulse rate variability validation, we can say that the video PPG provides satisfying estimation of PRV parameters, even though there were some issues during hand grip, probably due to the movements of the subjects. And also, the sympathovagal balance behaves as expected, with observed vagal activation during pace breathing and sympathetic activation during hand grip. For the future developments should be addressed at improve the robustness to movement of this method, and also to validate it in conditions closer to those of possible real-world applications. Thanks for your attention.
So then we move then to the last speaker, who is Francesco Branciforte from Politecnico di Torino, who is going to present us a study about the quality enhancement of dermatological images using GANs, a proof of concept.
Okay, thank you for the introduction, and good afternoon to everybody. And I'm so glad to be here to present our approach for quality enhancement of dermatological images. What are dermatological images? Dermatological images are images of skin lesions, such as melanoma or nevus, that are acquired in epiluminescence conditions. These images are usually analyzed by dermatologists that, analyzing the typical pattern of these lesions, are able to make a clinical diagnosis. This evaluation can be made in person or remotely. In the second case, we talk about teledermatology. Teledermatology is a new branch of telemedicine that allows a patient to obtain dermatological care from home. How it works? A patient with a device that is usually attached to the smartphone acquire an image of the skin and then send it to the dermatologist. The dermatologist then evaluate the images and then made a clinical outcome. These images can also be analyzed by eye-based system. This eye-based system can perform classification, segmentation, or normalization tasks. Are used usually as a second opinion tool for the dermatologist. Image quality is a key factor also for teledermatology and for eye frameworks. With high-quality dermatological image, we mean an image that has an eye contrast, that is sharp, that is without blurring artifacts or some invasive artifacts. High-quality images allow a dermatologist to make an accurate diagnosis because it can evaluate in accurate way the typical patterns of these lesions. In contrast, poor quality images can lead in possible misdiagnosis, compromising the patient's care. The problem is that the provision of high-resolution images from the patients in teledermatological cases is not always possible, due to, for example, not correct acquisition condition or due to, for example, the transmission protocol that not always include lossless algorithmic compression. The image quality is also so important for eye-based frameworks. In fact, high-quality images allow the model to learn the intricate patterns of these lesions. And this means an high generalization capabilities of these models. Poor quality images, instead, lead to an ineffective training of this model that became not so useful. The problem is that on the internet exists a lot of open access dermatoscopic images database that contains a lot of images, but not all these images has an higher resolution and the necessary quality to be analyzed correctly. So, in response to these needs, we propose as a solution a GAN-based tool that is able to doubling the image resolution and enhance the details of these images. In figure, we can see the overall pipeline of our work. We started from an initial pool of 30,000 images from the EasyCharkiv dataset. Then we made an image selection phase by an expert operator that selects only images that has a certain resolution and that does not present artifacts that cannot be useful. Then we made a paired dataset preparation phase. In this phase, starting from the high-resolution images, we prepared synthetic low-resolution images. This paired dataset was then used to fine-tune our model, the Real SR GAN. Real SR GAN is one of the state-of-art GAN for super resolution that is made and designed only for real-world application, but it is not able to handle with the specific pattern of skin lesions. So we decided to fine-tune this model in order to handle and treat in a well way these patterns. Then we performed an evaluation phase of our model. One of the key steps of our pipeline is the construction of the paired dataset. In fact, to ensure effective model training, it is essential to generate highly authentic, low-quality counterparts, starting from the high-quality images. To do that, we implemented and adapted a degradation pipeline. This degradation pipeline includes some operations, such as downscaling, blurring, noise addition, or compression. The most important thing is that this operation are applied in different way for each image, and once or 2 times. In this way, we obtain a dataset of synthetic low-quality images that has a very large heterogeneity. This allows us to obtain a source domain dataset that has a very high heterogeneity, and a target domain dataset of high-resolution images that instead is very homogeneous. And this is a winning combination when you try to train in an effective way a generative adversarial network. In the slide are presented in the first row 3 examples of 3 high-quality dermatoscopic images. And in the second row, the synthetic low-quality dermatoscopic images that are obtained applying the degradation pipeline. To evaluate our model, we started from a quantitative evaluation. We calculated for a test, to a test set that is made by all of the images that were not considered in the data selection phase. And we calculated some no-reference and full reference metrics. As full reference metrics, so metrics that made a comparison between the generated image and the original image, we considered the PSNR, so peak to senior noise ratio, obtaining a mean value score of 38.62. That means that our model does not introduce too much noise in the generated image. And then we used the FC metric, the feature structural index metric. This metric, obtaining a score that is very close to 1, means that the generated image preserved the original structural information in the original images. Then, to evaluate the perceptual quality of these images, we implemented 2 no-reference metrics, the PICE metric, that is a perceptual image quality evaluator, and the MANICA, that is a recent metric that stands for multi-attention network for image quality assessment. As we can see from the table, we obtained lower score on the PICE metric for enhanced images, and higher score for MANICA for the enhanced images. This means that the perceived quality of the generated images is higher than the original ones. We also made the comparison, as we can see from the bar plot, between the enhanced images with our tool and 2 methods and 2 upsampling algorithms that are very popular, the bilinear and the bicubic algorithms. As we can see, our method outperforms the other 2 methods. We also conducted a paired t-test between the original score and the enhanced score, obtaining a p-value that is lower than 0.001, meaning that this difference is statistically significant. Secondly, we made also a suitability assessment. This was performed to measure the perception and applicability of enhanced images in eye and clinical evaluation. How we do that? We provided 60 images of varying quality levels to an expert dermatologist and to an eye expert. As we can see from the bar plot, we can see how for clinical evaluation, the enhanced images obtained the best score. So almost 95% of the enhanced images were judged as suitable for clinical evaluation. Instead, also for eye application, enhanced images obtain a score that is very close to the eye original dermatoscopic images. Troppo veloce. Okay. Finally, we conducted also a qualitative evaluation. So we checked, zooming in, if our tool preserved successfully the specific pattern of these lesions. In the slide, we can see in the first row 3 examples from the EASY tested dataset. That is the dataset that contains all of the images that were not considered in the data selection phase. And in the second row, a dataset, 3 examples from a proprietary dataset that was acquired at Ospedale della Carità di Novara. As we can see, I don't know if the resolution of the projector is enough to appreciate the fact that the zoomed in box is more sharper and more clear. demonstrating how this tool is able to make this detail even more sharper. And this could lead in an higher confidence for the dermatologist and higher performance for eye-based tool. Now we are actually working to further improve this promising tool. Especially we are working on an extensive testing phase of the proposed method with other further datasets. We are trying also to optimize and customize the gun architecture, maybe introducing some last function that could focalize on the perceptual quality of the images. And finally, we are investigating the use of this tool as a pre-processing step for classification, segmentation, and color contrasty frameworks. That's all, and thank you for your attention.
So thanks to all the speakers that I will kindly invite to join us on the stage so we can open the discussion for this session. Okay, thank you very much for your presentations. And the session is now open for discussion. If there is any question from the audience. Yeah, there is one over there.
It's a question for the last speaker. If I understood correctly, you compare your GAN method with other oversampling methods, but you didn't perform any deblurring technique. So I'm not surprised that perform better, because the other cannot recover resolution if you don't apply deblurring. Is that correct, or I misunderstood your presentation?
Thank you for your question. If I understood well, you asked me if we tried to applying the blurring algorithm instead of this advanced tool. Yes, of course, we tried. The fact is that this tool is able to do two things. One, that is double the resolution. So it means that if you have an image that has, for example, a size that is lower than the input size of a network, to fit that image in the input side of that network, you need to upsample that image. If you upsample that image with standard upsampling methods such as B-cubic and bilinear, you are not able to obtain high detailed images. This is the first feature. And the second feature is that this tool is able to do this and then also to enhance the detail. And this increment in perceptual quality is not possible to obtain with a simple deblurring algorithm.
There's another question there.
I have a question for Dr. Moscato. So, your presentation was really interesting, so thank you. I have a curiosity about the quality of the data, because you have used Empatica, and we know that for the application in real world, there are not so many options. Probably this is the only one that can give you the raw data of the EDA signals. So the others are not, maybe are probably with poorer quality. But I've noted that you have a lot of dropouts for the PPG, and instead only a few for the EDA. Is it correct?
Less amount of PPG sessions available for art rate variability analysis than the EDA. Yeah.
Right. Is this because the quality of the EDAs was better, or just because?
Because of different approach applied to the two signals. Because for the PPG, I applied a classifier that that I developed to select only the pulses that can be reliably used for heart rate estimation by training and test a machine learning algorithm. While, so if a pulse has not a good quality, it is discarded, and that's it. While for the EDA, I used an algorithm to detect, yes, the bad quality segments, but I haven't enough time to explain it. I replace the bad quality segment simply with a linear interpolation. In general, I also compared the percentage on the whole signal for both PPG and EDA, the percentage of good quality segments, and EDA as a higher percentage of good quality segments rather than PPG. But that's why I were able to retrieve the higher number of sessions useful for EDA analysis.
And how did you detect the artifact in the EDA?
In the EDA, I used an algorithm from a researcher of MIT. It was a work presented at a past EMBC. Okay. Taylor, the first author was Taylor, the last author was Picard. Mm-hmm. And it's a Python, it's already available in Python, and I simply use it.
Okay. Thank you.
Thank you very much.
Are there any other questions from the audience?
I have one, a quick one for Andrea Costanzo Palmisciano. Yes. So basically, you were in your presentation, you studied a protocol to elicit some autonomic responses in different conditions by using two different techniques. So I would like to ask, I mean, which is the advantage of using this kind of video technique despite being non-contact, and how would you cope with some difficulties in analyzing these kind of signals in challenging conditions, for example, movement or something like this?
Yes. Okay. The video PPG technique, other than being non-contact, so non-invasive, can be more bearable by patient. Let's say you don't have to wear electrodes or something on you for, let's say, more than long-term monitoring. So I talked at the beginning of the presentation about monitoring of chronically ill patients. So we're talking about, let's say, home monitoring, so 24 hours, 7 days a week. So something very, very light for the patient. So in my opinion, this could be a great advantage of this technique. Of course, there is a lot of work to do to make this technique suitable to deal with movements that in daily life are normal. So first of all, this is of course a work in progress, and we did not implement, but we thought about some more advanced techniques to deal with these movement artifacts.
For the video processing?
Yes, for the video processing, and let's say both for video processing and then for signal processing, because of course these artifacts are in the video and in the signal, so it is a twofold problem. Thank you.
Hey, this is, yeah. So I have one question for the last speaker. Actually, two questions, one for the last and one for the third, but I start from the last. Like in your work, like the image didn't work. That is my question. Like the image, like that the dermatology were not saying, okay, this is better now to classify. And how does it deal with occlusions? actually, your algorithm?
Can you please repeat the first part of your question, please?
I didn't make the question right. So my question is, how does your algorithm deal with the occlusions, and in which image didn't it work, like that your algorithm produced image with more resolution, but the dermatology say, no, this is not better than an image with high resolution created by the machine?
Okay, our method does not perform so well when it tries to enhance an image that has a very, very low quality. The fact is that we selected and provide to the dermatologist enhanced image from a very different and varying pool of low quality images, okay? And in some images that starts from a very bad quality, it's not possible to reproduce a very high quality that is suitable at 100% for the dermatologist.
And how does it deal with occlusions? Like if you have part of the occluded.
What do you mean for occlusion?
Like that you don't have like the full image, like completely, like the part that the dermatology has to analyze, some parts, there are some signs that are cut. No.
This type of artifacts were not included in the evaluation.
Were not included?
No.
Okay, okay. Thank you.
You're welcome.
Okay, thank you. I'd like to ask a question to the second speaker, so Esther Bruno. So there are different types of filters that can kind of recognize these tubular structures, like the Hessian-based approach. Did you evaluate other approaches similar to this one, or not?
Thank you for your question. And okay, for now, this is a preliminary study, and we used this approach because we found an article in literature that used the same approach of the Hessian matrix to segment vessels that are the ramification pretty similar of the arborization of the neurons. But for now, this gave us good results. So we are trying to do the next step and to do, instead of a tracing of the neck, to do a segmentation of the neck, performing a local segmentation around the spines in order to classify spines and their different shapes.
Okay, thank you.
I have just a quick one for Miloš, if I can. I would like to ask one quick question to connect to what we were saying yesterday about gender bioengineering and sex and gender bioengineering. You have a substantial amount of patients, and you used also age and sex as features. Did you have a look at some gender-specific model, sex-specific model in your data? And another quick question is, the amount of features in the two models is the same?
Yeah, okay. Let's start from the second one. Yes, the amount of features in the both models were the same. They were first selecting by feature selection using information gain index. And in the both of set of features were included both sex and age. So, and in the end, they were not present in the final models. Okay. Thank you.
I think we are running out of time, so I conclude this session. I would like, yes, if you just can wait here for a few minutes to make a small communication. In the meanwhile, I would like to thank you for attending and for contributing to this fruitful discussion during this session. So if you just can wait here a few more minutes to have a communication from the organization. Thank you very much again.
Sì, per tutti quelli che hanno il tour dei laboratori, vabbè, dovevamo partire 5 minuti fa, però insomma fate il prima possibile per favore, e ci troviamo all'ingresso, mentre per i tour culturali alle 5 sempre in ingresso. Ci siamo 3 di noi, io sono per il laboratorio di bioingegneria in movimento del DIS, ci sono altre 2 ragazze per gli altri laboratori e poi altri 3 ragazzi invece per i tour culturali. Beh.